Morning. Today we're going to talk about trigonometric limits, and there's something called the Squeeze Theorem, and I will include links for additional videos for Squeeze Theorem, as well as knowing important trigonometric limits. There are a couple that you'll just want to memorize here. So the Squeeze Theorem, you can consider a function trapped between two functions. So if the function is between the two functions on the interval, it looks like this. Okay, so it's trapped between them. The squeeze theorem applies when it's not just trapped, but it's squeezed. So the top function and the bottom function get really close to the function you're looking at in the middle. This leads us to something called the squeeze theorem. If for x not equal to c and some open interval containing c, we can put a function between two functions and squeeze it at that point where it's not defined to evaluate a limit there. Okay, so what I'm looking at here for this first problem is the limit as x approaches 0 of x times sine of 1 over x. We can't do this because at 0, 1 over x is undefined. Okay, so I can't use the product rule like we did before, so I can't just substitute it in. What I need to do is a little work here. I need to find two functions that work to squeeze this. Okay, now here's what you know. Sine oscillates between 1 and -1, correct? That means the absolute value of sine has to be less than or equal to 1. If we multiply both sides by the absolute value of x, we end up getting the absolute value of x sine of x is less than or equal to the absolute value of x. Okay, I can split this up, and I know we haven't done a lot of absolute value equation work here, but that means the negative absolute value of x should be less than or equal to x sine of 1 over x, which is less than or equal to the absolute value of positive x, or positive absolute value of x. Now, the graph of the absolute value of x looks like this. Okay, so the limit as x approaches 0 in this is going to be 0. And I'm going to write this differently. So the limit as x approaches 0 of the absolute value of x equals 0. Okay, and then the negative absolute value of x looks like this. So the limit as x approaches 0 of negative absolute value of x is the same as pulling this negative up front, but that's also 0 there. We can apply the squeeze theorem then, because we know that this is between these two values, and so since they're both 0, we can say the limit as x approaches 0 of x sine of 1 over x is also 0. THM is abbreviation for theorem. Kind of weird. I get it. I'm going to show you the graph just so you can see what it looks like. Here's our absolute value functions. They both get close to 0, and x is between, x sine of 1 over x is between those. So that's how the graph is shown here. Like I said, I'm gonna link some more examples in there that other people are doing. They might do a better job of explaining it than me, so I'll let you see those. Moving on, important trig limits. The limit as theta approaches infinity of sine of theta over theta is 1, and the limit as theta approaches 0 of 1 minus cosine of theta over theta is 0. Memorize these. There's a little proof here looking at kind of how this works out. You can check it out. Sorry, there's a theorem there. There's a proof in your book. So cosine of theta is less than or equal to sine of theta over theta, which is less than 1. So that is their squeeze theorem that they're using to prove this particular one here. And then this kind of goes along with it. Okay. So this next example tells us to investigate the limit as h approaches 0 of sine of 4h over h numerically and then exactly. Now, to do it numerically, that's what we did with those tables, and I'm not actually going to show you this work here because I would rather have you do algebraic manipulation because it's faster. But they're talking about looking at the left-hand and right-hand limits. So when we did left, we picked values getting close to 0, so like 0.1, 0.01, so forth and so on. And then we did the right side to get x, sorry, this would be negatives, 0.1, 0.01. Okay, so that's how you would do it numerically, back to what we did a couple sections ago. But algebraically, sine of 4h over h, I'm going to do a little bit of manipulation because this is not possible to use substitution. To do that, I'm going to do a little manipulation because I want this 4h to match my h over there. So I'm going to multiply this fraction by 4 over 4. What that does is rewrites it as sine of 4h over 4h times 4. Okay, if I let theta equal 4h, which is just a multiple of the value, I really have 4 sine of theta over theta. Now, if you go back to this one that you need to memorize, sine of theta over theta as theta approaches 0 is 1. So this is really the same as saying, sorry, h approaches theta. Not what I wanted. The limit as theta approaches 0 of 4 times sine of theta over theta, we can bring that out front and then do 4 times the limit of sine of theta over theta as theta approaches 0, which is 1, and we get 4. Now, if you check that over there, you should see that it's about the same. Okay, again, I'm linking in Squeeze Theorem. I'm going to apologize because that's something that if you talk to most calc teachers, they don't typically spend a lot of time on, but it did show up on an AP exam. But definitely make sure you memorize this here so you have that. Okay. Do your practice problems. Let me know if you need help. Have a great day.